I would like to welcome Brian Pailes. He's a principal engineer for Vector Corrosion Services, and he's going to talk about non-destructive testing to better define repair quantities, something that we all have a challenge with.
Well, thank you, everyone. And so, as said, I'm going to talk about non-destructive testing to better define repair quantities. So, what are the issues that we're all facing in here? Well, how do we properly determine these repair quantities? You know, right now, a lot of entities and engineers commonly use sounding and visual inspection, and we know that these will underestimate those repair quantities. When we actually go out to construction, we're going to be underestimating the true total quantity. And how does that impact us in the long term? So if we go out into construction with underestimating these quantities, how is that affecting us? And ultimately, it is with costly change orders and potential increased project duration, which is something nobody wants here on in their projects. Another thing that can be an issue is how long it takes from investigation or the last inspection till we actually get to those construction activities. It can be quite a significant amount of time. And in that time, obviously, deterioration will grow. With all of that, we're going to increase our quantities, and we're going to have issues come on the back end in construction. And one thing that I kind of always like to say here, too, is this isn't just for decks. You know, we kind of get into this thing to talk a lot about decks, but there's other elements of the structure, the superstructure, the foundation, the substructure. All of these can benefit from non-destructive testing as well to better quantify these repairs. What is really happening in our concrete when it starts to deteriorate? And I'm with Vector Corrosion Services, so obviously I'm kind of coming from a corrosion point of view, but really concrete deterioration has there's a lot of things that are similar even with corrosion and non-corrosion. Here we have a sounding survey that was done of a pier near a beam seat, and we can see obviously that the delamination has occurred. Obviously we have some sounding that has identified some delamination. So we obviously have a large near-surface delamination there that is caused by possibly corrosion, moisture exposure there. But really that delamination extends beyond that, right? That's only the near-surface delamination that we could identify with sounding. There is cracking and incipient deterioration beyond that. So if I went out there with a chipping hammer and started hitting that, it would probably end up growing to something like this. And this yellow part would be the part that is still deteriorated but couldn't be found by hammer sounding. And so obviously we're going to have an increase in quantity. So how do we really understand that? And there's more going on possibly beyond that as well. Maybe there's corrosion beyond that delamination deterioration that's active but hasn't created enough. Beyond the physical deterioration, we also potentially have some active corrosion beyond that. Now this is maybe actively corroding, but it hasn't quite caused physical damage yet. So if I go out there and just repair the yellow in the hatched area, am I really preserving the structure for the long term? Or if I do something to address all of this area, is that going to be a much better repair in the long term for this structure? So how do we better understand the yellow and red if we're just, and that's what I want to talk about with non-destructive testing. Concrete deterioration is a phase, right? So we start with regards to corrosion. We're going to start with chloride and moisture penetration into our concrete. That's going to reach the rebar and then start corrosion. And then corrosion's going to grow, expand, cause cracking and delamination in our concrete. And then eventually that will become spalling. And we see that, chain drag, hammer sounding, visual inspection on these tools that we use to evaluate this condition really can only identify kind of late stage in that deterioration curve. Visual inspection can only see visible cracks on the surface or spalling. Delaminations, really the late stage delaminations can be identified by hammer sounding and train drag. So how do we identify some of these conditions earlier? Techniques like electrical resistivity can identify if the concrete resistance is being lowered by chlorides and moisture. Corrosion potential, half cell, active corrosion. GPR can identify a wide swath of things, so maybe we could use GPR. Impact echo is better at identifying more delaminations earlier in that phase, and I'll talk a little bit about these. Obviously, visual inspection is important. I'm not saying that we need to step away from doing this or sounding. Obviously, we're looking for rust staining, cracking, spalling. Hopefully, we don't have piles that look like this, but this is pretty obvious for visual inspection to identify. Water infiltration, efflorescence. These are things obviously we need to be looking for. Sounding survey, still important. It's quick, it's easy. We go out with hammers or chains, and we can locate where all these near surface delaminations are. Unfortunately, because we're using the human ear to hear for these delaminations, we're limited by our human physiology. We can only find these late stage near surface delaminations. The nice thing about chain drag is false positives are rare, right? If you hear that hollow spot, that's a delamination that exists. It's pretty difficult for there to be a hollow spot without actually being damaged. In some weird, unique situations, it can occur. But for the most part, you run that chain over, you hear that sound, you've got a delamination. The problem is, though, you may run it over other areas that sound, but may actually have some incipient cracking and delamination that haven't grown to the level that would, so that you can visually hear it. So you may underestimate those quantities or miss areas by just relying on sounding alone. The first thing that I'm going to talk about is corrosion potential survey. This is a method that in the corrosion world we use quite a bit of, ASTM 876. And what we're doing is we have a reference electrode, and we're measuring the potential of that reference electrode versus the reinforcement in the structure. And the objective is, here we have delaminated concrete, right? We know there's physical damage there. We have to repair this. But where is active corrosion beyond what's physically damaged today? I want to know where that active deterioration is going to be going in the next few years. So if I do corrosion potential measurements on the structure in areas where I suspect maybe there's corrosion activity, I can use that measurement and identify where the probability of corrosion is high. And so, does that corrosion extend up in here, or is it just localized down to here? And then I can start to better plan my repair strategies so that I have a more durable structure over the long term. For a bridge deck, we can go do this on a bridge deck and, get the half-cell corrosion potential measurements from the deck, and you can see kind of the hot areas indicate where corrosion is active. And so we know, this bridge deck is pretty late in its service life. So it's pretty old, so there's a lot of active corrosion on this structure. If we overlay a sounding survey, right, we went out and did a sounding survey and we see, well, clearly there's a lot of delamination along the parapet, drainage areas, we're getting a lot of chlorides there. We see some delaminations around here, and we can see that there's this band where we have some spotty delaminations, but we see a lot of active corrosion banding that together. As an asset manager and a decision maker, I would need to decide, well, should I just go out and chip out and replace those patches, or should I address that whole area because that's going to be delaminating in the next few years? Or is this bridge so far along that really putting money towards this is kind of a waste and we should just replace it? So we can use this information to make better decisions with our money. And like I said, it's not just for decks, right? So this is a bridge structure. It's a little dark, I'm sorry, but you see there's some piers here and then the roadway. And this is in Springfield, Missouri. And the roadway, if you notice, kind of dips down. So when it rains and chlorides and snow melt, it kind of pools in this basin here and kind of exposes the piers to chlorides. And so we were asked to kind of look at where the risk for corrosion is. And you can kind of see here on the columns and then the footer, you see at the lower portion of the columns, there's a lot of active corrosion, these red spots. And you can see there's some hatching where there's some delamination. But we can say, the lower 4 feet of these columns are actively corroding. And we need to protect these so that they don't continue to deteriorate. An interesting thing to note is that the footer isn't very active, right? You would think, well, the footer is closer to the roadway, it's being more exposed to chlorides. Why isn't it as active as the columns? And this is actually a point I'll talk about here in a second, but it's cover depth. The footer was designed with better cover depth versus the columns. So while they have effectively the same exposure, that lower column area and the footer, the chloride progression hasn't reached the steel in the footer where it's reached the steel in the column. So cover depth affects the service life, and we're seeing that here where the corrosion is active currently. Maybe we do something preventative on the footer to prevent corrosion from starting, or maybe we just leave it and say, oh, we've got some years before we need to address this. And so that's kind of where GPR comes in with the cover depth. GPR is a very effective tool. It's electromagnetic survey of concrete, and what we like about it is that it can identify steel in concrete very well. Here's an image of a GPR scan. You see the steel shows up as really nice bright white hyperbolas here. And so we can use it to identify the layout of the reinforcement. We can measure the cover depth, which helps us in our service life, as Paul was talking about earlier. And we can also kind of do a qualitative condition assessment with it. Here you can kind of see these rebars are nice bright white, and these are very faded and attenuated. Well, the GPR signal is affected by a lot of things. If there's a lot of moisture in the concrete, if there's a lot of chlorides, if there's a lot of deterioration, it can scatter and weaken the signal. And so as a result, if I go around and I look at where my signal's weakened, that's an area of potential deterioration. And I stress the word potential here. A lot of people like to use GPR and say, oh, I'm going to go out and do a delamination survey, or I'm going to go out and find you, section loss. Well, GPR is good because it's affected by so many things, but I can't tell you if this area is delaminated, or maybe there was just a lot of moisture exposure there. Maybe it's near a drainage path. Now, that might lead to a lot of deterioration in the future, but that doesn't mean there's deterioration today. Using GPR as a tool for further investigation, I think, is really useful, but you have to understand and qualify that information and make sure you're not stretching it too far. Paul was nice to show this equation earlier, so he was able to bore you and I don't have to as much. So I don't want to get into the equation too much. It's the diffusion coefficient for chlorides. But what I want to stress about it is how I rearranged it for T. So what Paul was talking about was time to initiation of chloride diffusion, right? And really why cover depth is so important is because when you solve for time, depth to the steel is squared. So depth to your steel has an exponential impact on your service life of your structure. And that's really what I want to get at here, is that cover depth is extremely important. So if we can use GPR to assess cover depth in your structures, we can really get a good idea of the service life using things that Paul built. Those kind of models are very effective in that. And so this is a structure in that I was doing some work on in some columns, and there's some risk of low cover in these columns, and the low cover was then causing some carbonation corrosion, induced corrosion. And so here, we can use GPR on the columns and then identify areas of very low cover, and these are the areas that we need to address now. So using GPR, we can scan elements and identify these high-risk areas for early deterioration, do preventative maintenance on them now, and then that way, in the long run, we don't have to worry about the long-term durability of the structure. And so areas of low cover, are something that can be addressed easily and quickly. With the amplitude survey, that qualitative assessment I was talking about, the example I have here is actually, this is in Florida. In Florida, we have the benefit that we don't have de-icing salts, so our decks last very long. It's our substructures we have to worry about. As you'll see on this bridge, this is down in Naples, and you see there's a marina right here. This is on the west coast of Florida. So the ocean, the Gulf of Mexico is out on here on the left, and so people come in and put their boats in and take them out on the weekend, and then they drive over this bridge. Now, when you take your boat out of the salt water, you're supposed to wash your boat down. Nobody does that. And so what happens is they take their boat freshly out of the salt water and then drive it over this bridge deck. And you can see that on the eastbound lane of the first few spans of this bridge, there's a lot of attenuation of the GPR signal due to this. Now, is this all delaminated concrete? No. Is it high in chlorides? Probably. Is there some delaminations there? Most likely. But we have an idea of where that exposure is in that deck using just GPR, and we can locate, the DOT here needs to maybe we need to put a coating down in the first, 400 feet of this bridge. Maybe we need to mill and replace that section. But we can really identify where that exposure is occurring with the GPR. And that was it's a quick and easy tool, and it really identifies the extent of their problem there. Acoustic methods are really effective for finding voids or delaminations. Impact echo is a method where you take an impact source and you create a compressional wave in a slab, and that compressional wave will vibrate at a frequency. And if that frequency is related to the slab thickness, then we know that resonant frequency, we're in good sound concrete. If we have cracking or delaminations, that frequency is going to vibrate at a much higher frequency, and so we can identify delaminations through this method. And really, it's just a fancy chain drag, right? That's all chain drag is doing. You're inducing an energy and listening to that frequency. Well, your ear can only hear a certain frequency range, so we can use sensors to listen for a much broader frequency range. So we can find the delaminations much sooner than when they become a large-scale delamination that chain drag can find. We can also use those same compressional waves for wave velocity. So horizontal waves traveling between sensors, we can identify the speed of those waves. And if there's cracking, that's going to affect that wave speed, and we can identify cracking or weakened concrete because of that. And so using these acoustic methods, we can really understand the properties of the concrete. And one of the things that we can also do is identify the in-situ compressive strength. And so if there's deterioration or weakened concrete, acoustic methods can identify this due to the relationship in wave velocity versus strength. And so it's a very effective non-destructive tool. And so it can be run out on bridge decks or on substructure elements. And so here is a deck tester, NDT Corporation, works with VCS. And so they have sensors on wheels that rotate, and they just walk and make the impacts. And they're doing wave analysis to identify not only doing the impact echo, so looking for delaminations, but also the wave velocity to find the in-situ compressive strength. So here's kind of an image of how their system works. So the impactor is here. They have a trailing sensor for transverse cracking. They have the longitudinal cracking is on the side sensors, and then impact echo is identified in the first two sensors as well. So by going over a structure, they can identify where weakened concrete due to cracking and delaminations exist, and then develop a map. And this will be ultimately more accurate than just chain drag alone, because you're identifying those delaminations and cracks that chain drag just can't find because of the limitations of our ears. This can help to better quantify those repair quantities in a deck or a substructure element or whatever it is you're testing. Like I said, with substructure, that was the deck wheel for deck testing. Here's a handheld unit with the sensor array and the impact source, and we can do it on, this happens to be in Milwaukee, and this is a tunnel looking at the wall there. And so here's our array and acquisition system. So what we're looking at here is, what are the results we're really looking at? And so we have a joint, and we went out, the engineer were working with sounds, and so around a joint, these highlighted areas, this blue, that was delamination identified by sounding, and then they found another delamination here by sounding. Well, okay, that's great. Well, but is that the extent of all of our damage? Well, if we go out and do delamination testing by impact echo, that grew all of a sudden. So before we were here, now those delaminations actually extend beyond that. So we have a little kick out here, and then this area is actually much larger than we anticipated. So already we have a significant growth in our area of delaminated concrete. But not only that, so that's just delaminated concrete. What about concrete that is still in more incipient phase? What if we looked at the compressive strength? Maybe there's some cracking that's starting to form. So if we look at the compressive strength of the concrete as well, the in situ compressive strength, you can see that there's some weakened concrete a little further out beyond this and here. This is where that delamination's really growing too. And so our total repair quantities are now going to be this area. If we just had relied on sounding, we would have underestimated the repair quantities easily by a half, even by half, or even more. And so using a technology like an acoustic impact echo surface wave velocity, we can better refine that quantity and understand what's going to need to be repaired. One thing I'll kind of touch base, I'm a little running out of time here, but infrared thermography is another NDT tool that's used out there quite a bit. Effectively, delaminations have different thermal properties than sound concrete. As a delamination occurs, it's an air gap between the sound concrete, so that'll heat up faster in the morning sun and it'll cool down quicker in the evening. And so using that technique, using that understanding of the thermal dynamics of the delaminations, we can go out and use infrared cameras to quickly assess where delaminations are occurring on structures. Generally, the results are very similar to chain drag, your near surface larger delaminations. Your equipment is an IR camera. They come in different forms. Now they're on planes and drones and all sorts of things these days. This is just a basic handheld, the olden days of like 3 years ago. Here's a dam face, and you can see I highlighted two areas. This is kind of first thing in the morning, and then you can see this spot here as it's heating up. You can see this hot spot up here. So, obviously we can see that there's a delamination. So we can set the IR camera up on a tripod. We can go off and do something else. It's snapping away, and then when we come back, we can kind of see where the delaminations are. So a little bit of efficiency in the site. This is just an example of a project in Minneapolis that we did. Effectively, they'd done hammer sounding several years ago, found all the delaminations, but then several years went by before they were able to kind of get the bid documents out. And so they wanted just some quick verification. How big have the delaminations grown beyond what we last sounded? So went out and did some quick IR shots in certain areas where you could. This bridge, due to the structure of it, you couldn't do everything, but there were some easy areas that you could kind of just shoot with the IR camera and say, okay, there was a delamination there. Are we seeing it any bigger? How much bigger? So that we can increase the quantities before we go out to bid. With that, I open it up to questions.
So the question is, if I'm doing a GPR and you did potential delamination, question will be if I have a black bar or epoxy bar or whatever, how do you, from your perspective, how do you determine whether is that good idea to remove this anyway or just keep the whatever the soundar or whatever you're using, the hammer, the actual delamination? How do you go with this phase to determine what do I need to remove from practical point of view?
Like the quantity of it, or is it more, your question more, should I remove it or let it go for a few years?
Well, okay, if for contractor, is he gonna do it or not? It's, remember from owner point of view, it's kind of like we're gonna pay him. The question is this, if he's using his hammer, is not taking it out, that means it's probably good shape. But you show in GPR potential, I don't know how long.
So you're kind of saying, okay, right here, we're showing some attenuation, right? Should he chip that out now or not? And that's a very good question. What I would say to that is one, you shouldn't just be relying, right, on just the GPR alone, right? We did a sounding with this as well. I don't have that data on this one, but I would say you want to do, with any kind of assessment, at least one, you never want to rely on one technology, right? You never want to just rely on GPR. You never want to just rely on sounding. But if you did both with half cell or just GPR and sounding, so now I know where my delaminations are that are near surface that I found in sounding, and then I know where potential other areas are with GPR. Now, I may increase those delaminations according to the GPR, because the GPR will help with the sounding, will help me say, well, these areas with this kind of attenuation, they're relating to the delaminations. I'm going to probably say then that these areas that I found in GPR that I didn't find with hammer sounding, let's just go ahead and replace those, but then some other areas I'm not going to touch now. You need to kind of have a multiple tool approach so that you can quantify what you need to replace now versus what you want to replace in the future. So I think to say GPR is going to give you that understanding alone, it's not really. I mean, I wouldn't go chip all this concrete out, right, that's on here. I would say we need to look at where the delaminations are they, and where that's going to progress, and then better define those bounds. But I would say that the area that we're going to have to remove is much larger than what the sounding's going to find, but it's not quite as much as the GPR found. So there's some refinement in how you quantify what's replacement and what is maybe a preventative maintenance area. And I think what the point I want to say about GPR is that it's hard to tell which one is which from GPR alone. So that's why you need a second method to kind of say, these are the areas I would like to focus on with something else. So I need to maybe take a core here, or I need to maybe look at half cell in this little area. So it can limit your scope of other methods, but I think those other methods are still important.
Well, Brian, I agree with you. I think you shouldn't hang your hat on one particular data set, particularly with regard to GPR or even impact echo for that matter sometime. My question to you is, as an owner, as I'm trying to make a decision, right, with this, let's say, or half cell, this and half cell, right? You're identifying certain area for removal and whatnot, but what happens to the other area that you don't remove, which is chloride contaminated? What do you suggest to the owner? What do you do with those?
Well, I think that's a good point, right? You have exposure in a lot more places, right? It may be active, and I think that's a good point with the foundation that I showed, right, Siva? It's, you have chlorides in this footer, right? It may not be active today, but there are tons of chlorides in it. And the question comes, well, what do we do? We're going to obviously do something more physically invasive to the columns, but what do we do to the footer? And the level of preventative, I think, comes down to, one, the owner's past experiences and what kind of budget they're working with, right? Some owners might say, well, I've got money to spend elsewhere. I can't afford to work on something that's not corroding today, so they may skip this part. I would say at the very least, I would try to, moisture is going to be the enemy here, right? Can we put like a silane or something on the footer to help keep it drier, right? Okay, we have high chlorides there, but if we can limit the moisture content, even with high chlorides, we'd limit the corrosion rate. So I think thinking of options like that would be helpful, but I think it's a really important thing to answer, because you're right, we do have chlorides in there, and if we do nothing, it's just going to become the columns in the future. But if we do something cheap now, we can extend the life of that. And I think looking at those options, like, okay, can we do a sealer? You could think about cathodic protection on this. I think it's probably a little early in that footer's life for that, but that's a potential option. Or, looking at the exposure environment or something like that.
And one of the comment I would suggest is maybe do a service line modeling, where you actually really figure out what the diffusion, what
Right.
time, and what the deterioration is going to be. Then you have a holistic solution to the entire structure instead of just doing part by.
Right, absolutely. And doing Paul's modeling, you can say, well, when is that going to be a problem, right? If it's in 5 years, okay, we need to do something. If it's in 50 years, all right, forget it. Yeah, exactly.
Thank you, Brian. Good job.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.